Yo, what's up everybody? Welcome to another stream. Today we're going from Bora Bora to Fiji. This should be like only an hour and a half to 2 hour flight, give or take. So let's not waste any time and let's get started. But flight plan, let's prepare but everything might sound very echoey and you can imagine some noise in the background like my dog that is behind me. Okay, cool. So yeah, here's our plane. We're just gonna we're supposed to get in. Fuel truck, bridge, here, like out of payload here. So we need 99 passengers. Everybody for today, and how much fuel are we expecting getting on? Fuel today, about 88.88. And yeah, everything's on board. Cool. And aircraft. Everything is good here. Make sure. Okay, let's see how to payload first, then fuel. So we're looking for about 184 or 40.56, give or take. Yep, that should work. Cool. Now I got everything. Got everything that we on. Minus. It's good. That's just Stop. 1, 7, 5, 4, 7, 9. Now, also adding one bar. We're gonna go straight to the arrival because Also, let me show you guys the flight plan for today. It's a very short flight. Yeah, let's go. The flight plan. butterfly looks like green. So, 1, 7. Looks like this is a Alright guys, on our flight.
It saves us 60 tons.
should we listen to Concorde first? Learn about the Concorde, or do music right now? I'm thinking to do music. I'm thinking to do learn about the 177, and then we can do music later. Yeah, let's do 77. We'll learn about the phone. 20,000 feet and climbing. And then we'll learn about engines and 787. Cool. So, alright guys, you guys will see a display capture.
Real Engineering is brought to you by the Curiosity Stream and Nebula Bundle Deal. Sign up now to watch the hour-long version of this video linked in the description. If you were not paying attention, you may not have noticed the revolution happening in the airline industry. The days of attempting to build bigger and bigger airliners like the 850-passenger double-decker A380 and the 660-passenger humped 747 are gone. The behemoths are simply being outcompeted by a new generation of planes. Many mourn the slow demise of these iconic planes, but you are benefiting from this change. The entire nature of air travel has changed to benefit you and your needs. Your local airport has more direct flights to distant lands than ever before, and the price of those tickets are cheaper than ever. Connecting flights are becoming rarer and rarer as this new breed of plane takes over. The plane at the forefront of this revolution, the 787 Dreamliner, a $30 billion bet on the future of the airline industry. Boeing sat at the poker table and pushed all their chips forward, an all-in bet on a radical new future, and it paid off. The 787 revolutionized not only how the airline industry operates, but how the future of planes will be designed and built. This is the breakdown of the 787's materials. By weight, 55% of the 787 is made from composite materials, like carbon fiber.
audio out of all. Yeah, audio option. So, okay. Got it. Cool. That was fun. So, I want to know how Clyde does, what is it, what if I turn up the sound just a tad? Hold on. Wow. Okay. Yeah, that works actually. Um, if I speak really quietly, guys will hear me. Let's get it out. Cool. What if I refer to next one? Audio. Yes. Cool. Now, if I just do the basic audio, guys should, oh, it reached 28,000 feet. Let's start at Mach 2. Fine. 6,000 feet. Max climb. Hello. First, afterburners alive. Wow. Let's go. Okay, cool. And we passed Mach 1, everybody. Let's see. God. 2 hours and 48 minutes to go. 30,000 feet. Outside of my side. That's pretty good. Yeah. Though I do not like that echo audio that all these audio should be off. Agreed. Yeah. Yeah, that's what audio. Okay. Yeah. It's weird. Cancel X-Plane audio and normal audio. What that sound like? Ramps moving confirmed. I want to just try something. Okay, yeah, that actually works. Nice. 40,000 feet and climbing. Alright, so let's get back to our video.
Reinforced plastics, making it the first commercial airliner made primarily with this new age material. The 787 is rivaled only by the Airbus A350 XWB, introduced 4 years after the 787 in 2015. So, why are composite materials so desirable for the airline industry, and how has the 787 made the most of their advantages? Composite materials are made up of two or more materials. Take carbon-reinforced plastics. They are composed of extremely strong carbon fibers bound together by a plastic resin. Carbon fiber, made up of thousands of tiny thin fibers of carbon, is incredibly strong in tension, up to 5 times stronger than steel and 1/5 of its weight. But these tiny fibers can't create a solid part by themselves. This is an image of a human hair beside a carbon fiber. The carbon fiber is the smaller one, and just like a human hair, they can bend and flex and separate very easily. So we need to first bind them together with a plastic resin to form a solid material. Otherwise, they just form a strong but flexible fabric. That flexibility as a fabric is exactly what makes composites so useful when creating the precise and elegant curves of a plane. With the right tooling and designers, composite components can be made into almost any shape imaginable. In the past, a disadvantage of making large aircraft components from composites was the time taken to manually lay up parts, where layers of carbon fiber and plastic resin had to be carefully constructed. It required skilled technicians and was inherently difficult to scale to the production quantities Boeing needed. To get around this, Boeing uses automated tape laying to produce massive aircraft sections. The 787's fuselage is created by wrapping a carbon fiber tape impregnated with a plastic resin around a rotating mold of the fuselage. This machine precisely controls the overlaps of the tape and the orientation of the fibers to ensure we are getting the most out of the carbon's tensile strength to resist the internal pressure loads and the longitudinal bending loads the fuselage will experience. One of the problems with this manufacturing method is that the part needs to be placed inside an oven to cure the resin. This hardens the plastic and creates a solid composite structure. Ovens the size of a wide-body jet airliner fuselage are not exactly common, and this is often the limiting factor on parts made this way, and requires massive upfront investment to build a customized oven large enough to fit the part. But the benefits are well worth it. The first and most obvious is the strength carbon fiber provides. Previous generation airliners are typically pressurized to an equivalent of 8,000 feet. That's the same height as Mount Olympus in Washington state. High enough that the lower pressure would reduce your oxygen intake and your stomach will bloat as the air inside is higher pressure than the outside. This is uncomfortable and exacerbates the effects of jet lag. But thanks to the 787's stronger fuselage, it can increase its internal air pressure to an equivalent of 6,000 feet, 25% lower in altitude and about 7.3% higher in pressure. That may not sound like a lot, but it goes a long way in making the journey more comfortable. And at the very least, the person next to you won't be farting as much.
This game, you're not ready for it.
You're in the middle of this beautiful sci-fi environment, and you're seeing intrigue, the espionage, the alliances form.
Less farting is always nice, but my favourite benefit of the stronger fuselage is the absolutely massive windows. This is the 787 window, and these are windows of some equivalent aluminium airliners. They are absolutely massive. In aircraft made primarily from aluminium, having holes this large in metal panels would result in the buildup of stress at the window boundaries, as the stress contours have to deviate around the window. This stress does not exceed the material's strength, but over repeated pressure cycles, tiny imperfections in the metal can grow into even larger cracks and eventually fail. Holes this large in an aluminium airliner would severely shorten the plane's flying career before it needed to be fixed or disposed of. Kind of like how cracks in McGregor's leg shortened his career. But it's not a problem for the 787 thanks to composite's relative immunity to fatigue. You could kick Dustin Poirier's kneecap as many times as you like with carbon fibre shins. The carbon fibre construction provides plenty of benefits for the airline operators too, because the fuselage is just one massive part. Boeing was able to eliminate all joints and all the fasteners needed to join them together. Sections that used to be made up of 1,500 aluminium sheets riveted together using 40 to 50,000 fasteners are now just one massive carbon fibre section. Carbon fibre's strength to weight ratio already makes the fuselage lighter, but eliminating joints and fasteners makes it even lighter again. The reduced weight reduces fuel burn, but this fuselage is also incredibly aerodynamic because it doesn't have thousands of little bumps and ridges all over it from those joints and rivets. These surface imperfections make the plane's surface rough and cause it to disturb more airflow, increasing parasitic drag. Composite materials help reduce drag in other ways too. One of my favourite things about the 787 is its elegant wings. The main structural member of a wing is the wing spar. Its primary role is to resist the upwards bending force during flight. It's essentially just an I-beam, a shape optimized to resist bending loads. The wing spars of the 787 are constructed from carbon fibre composites, while the ribs, the structural members connecting the two spars, and that support the wing skin are machined out of solid aluminium plates. The structure the rear and forward wing spars form with ribs running between is called the wing box, and it forms the main load-bearing structure of the wing, while also being a literal box for fuel to sit inside. The carbon fibre composite spar provides the wing fantastic strength. Strength is quantified by the force required to completely fracture material, but carbon fibre composites have another important quality that makes them perfect for aircraft wings: their maximum elastic strain. There are two types of deformation: elastic and plastic deformation. Elastic means the material will snap back into its original shape after the load is removed, like an elastic band. Plastic means it will permanently deform and won't return to its original shape once the load is removed, something we don't want to happen. This is permanent damage. Carbon fibre composites can deform further before they strike this plastic deformation zone at about 1.9%, while aircraft aluminium begins permanently deforming at less than 1%. That means we can bend carbon composites further before we need to worry about permanently deforming them. And that means we can make our wings super flexible. During flight, the wingtip of the 787 can move upwards by 3 meters. That sounds like a lot, but in order to get certified by the FAA, every plane needs to be able to handle 150% of the plane's absolute maximum expected load during flight for 3 seconds. And during that test, the 787's wing bent upwards by 7.6 meters. That's a great deal of bending, despite carbon fibre composites being stiffer than aluminium, meaning it takes more force to deform the same volume of material. But critically, 787 wings are not the same shape as their aluminium counterparts. This ability to withstand greater bending allowed engineers to make the 787's wings with a much higher aspect ratio. Aspect ratio is the ratio between the wing span and the mean chord, or wing width. A high aspect ratio would be a long, skinny wing like a glider, while a low aspect ratio would be a delta wing of a fighter jet. A traditional airliner has an aspect ratio of about 9, like the 787's predecessor, the 777. But the 787 has a massive aspect ratio at 11. This is what causes the 787's wings to flex so much during flight. Composites are actually stiffer than aluminium, but their ability to withstand high deformation allowed the engineers at Boeing to create a much higher aspect ratio wing, a longer, narrower wing that would bend more. But this
It's everything you wished for. Your site traffic is skyrocketing. Until this.
comes with some huge benefits. The planes with the highest aspect ratio are gliders. For an unpowered plane, the highest priority is minimizing energy lost to drag. This allows the glider to stay in the air for extended periods with no engine. These types of aircraft typically have aspect ratios greater than 30, and these aircraft have the lowest drag penalties as a result of vortex drag. This is the drag caused by air mixing from the high pressure zone under the wing with low pressure air above the wing, forming vortices at the wing tip. By spreading the area of the wing over a longer span, we minimize the pressure that drives this mixing at the wing tip, and thus minimize the energy lost to the vortices. Normally, higher aspect ratio wings have lower internal volumes. For an unpowered glider, this isn't an issue. But for a plane that needs that storage space for fuel, it is. Less storage volume for fuel means lower range, and one of the primary goals of the 787 is to be an efficient, long-range aircraft, capable of allowing airliners to open new routes that were once deemed impossible. Thankfully, modern planes like the 787 use a new kind of aerofoil, the supercritical aerofoil. Older aerofoils look something like this, a reasonably symmetric design with a sharp nose and gentle curves on the upper and lower surface. And this is a supercritical wing. The leading edge is blunter with a larger radius, the top is relatively flat, and the lower portion has this strange cusp at the back. This aerofoil has much more useful internal volume thanks to its blunt leading edge and larger thickness to chord ratio, helping solve our low internal volume problem associated with high aspect ratio wings. The supercritical wing was first tested by NASA on a modified TF-8A Crusader, and you can really see the similarities in design ethos between the experimental plane's sleek wings with the 787. But increased internal volume is not why NASA developed the supercritical wing. NASA developed it to delay the onset of shockwave formation over the wings. When air travels over a wing, the air on top accelerates. This means that even though the plane itself might be traveling below the speed of sound, the air over the wing may break it and create a shockwave. This shockwave decreases lift and causes an increase in drag. This kind of drag is called wave drag, and planes need to fly below the speed this occurs at. The speed is called the critical Mach number. The supercritical wing was designed to increase the critical Mach number. The flat top of the supercritical wing means the air does not accelerate as much as it would over a classic aerofoil. Of course, this causes a loss in lift because that fast-moving air is causing a drop in pressure on top of the wing. To compensate, supercritical aerofoils have this concave curvature underneath the wing, which causes an increase of pressure there to compensate. This increase in pressure does not affect the critical Mach number, while the larger radius of the leading edge increases the lift generated at higher angles of attack. This is because air struggles to follow the tighter turns of a smaller radius leading edge, which causes earlier flow detachment and stall. The larger radius delays this flow separation. This aerofoil's shape changes continually as you travel the length of the wing, twisting and curving in computer-calculated precision, optimizing the wing shape to be as efficient as possible, and Composites provided the engineers with the confidence that these shapes could be manufactured. The skin is simply laid down on a mold with automated tape laying once again. We don't have to beat metal into shape each and every time we want to recreate these delicate curves. The fibers of the wing have even been laid in specific patterns to tailor the stiffness of the wing in different areas. This means the wing deforms exactly as the 787's engineers want it to as it gains speed. So, the wing shape actually changes during flight to better suit the needs at different speeds. This is called aeroelastic tailoring and is the forefront of state-of-the-art aeronautical engineering today. The 787 also features a novel device designed to reduce turbulent flow over the tail of the aircraft. Two types of flow states exist in aerodynamics. Laminar flow occurs at low velocities and is characterized by fluid layers flowing smoothly over each other in neat, orderly layers. Laminar flow is predictable and non-erratic and does not create significant drag. Turbulent flow is far more common, but still very little is known about how to predict its behavior. It is very difficult to control because of the formation of small vortices called eddies in the flow, making the flow highly erratic. Turbulent flow occurs at higher flow velocities and causes a significant increase in drag. At cruising speeds of 80 to 85% of the speed of sound, turbulent flow is ultimately unavoidable, but we can work to minimize it. Boeing has developed a technology that helps them delay and control the formation of turbulent flow called hybrid laminar flow control. Details on their implementation of the technology are sparse. This technology is capable of reducing fuel burn by as much as 30%, and so companies are keeping their research extremely secretive to keep their competitive advantage. Here's what we know. In the late 80s and early 90s, NASA and Boeing began investigating a suction system in the 757 that would draw in boundary layer air. That is, the layer of very slow-moving air that clings to the surface of moving objects. The outside skin was permeable to air through tiny perforations, too small for the naked eye to see. Manufacturing the permeable surface while also keeping the tiny holes clear of debris is one of the many challenges with this technology. The outer and inner skin were then attached to an elaborate plumbing system that was connected to a turbopump which sucked air from the boundary layer of air that would form along the plane's surface. By doing this, they could drastically delay and reduce the size of the turbulent flow, and in turn, reduce the drag on the plane. There is no space for this ducting system inside the wings of the 787, but from what we do know, it is inside both the horizontal and vertical tails. However, the only clue of their presence are these tiny doors, whose purpose are a mystery to me with little to no information available online, a testament of how advanced this plane is. Composites give plenty of advantages, but it does come with some disadvantages. When we examine the plane's composition, one material jumps out at me. 15% of this plane is titanium. That's much higher than normal. Titanium is an expensive material, so they must have had a good reason to use it over aluminium. Aluminium is typically corrosion resistant when it's left on its own, but when it is placed in direct contact with carbon fiber composites, something strange happens. The aluminium begins to corrode incredibly quickly. Something about carbon fiber causes aluminium to oxidize and fall apart. Carbon fiber is like aluminium's kryptonite. This phenomenon is called galvanic corrosion, and it happens when two materials that have dissimilar electric potentials or nobilities are placed in contact with an electrolyte, like salt water. If we look at the galvanic series, which quantifies materials' nobilities, we can see that graphite is very noble, on the far end of the left scale, while aluminium is quite far to the right. When this occurs, an electric potential forms between the two materials that causes the two materials to trade electrons and ions, which results in the anode being eaten away. This effect is made even worse when the surface of the more noble material, the cathode, is very large in comparison to the less noble material, the anode. Say, for example, when carbon fiber composites are fastened together using aluminium fasteners. To avoid this corrosion, the engineers needed to pick a material closer to carbon in the galvanic series, and the closest suitable metal was titanium. This has been a huge source of cost in manufacturing, Boeing's production cost was higher than its sales price for quite some time, meaning they were making a loss on each aircraft sold. This is fairly typical for new airliners, as R&D and manufacturing tooling costs take time to recoup, and companies like Boeing typically spread these costs over a period of time on each plane, instead of just having a massive negative balance sheet in 1 year. But because the 787 was so radically new, these sunk development costs, called deferred costs, were expected to reach $25 billion before Boeing even reached a break-even point on each plane sold, where the cost of manufacturing equaled the sales price. In comparison, the Boeing 777 reached $3.7 billion. To recoup costs as fast as possible, it was essential that Boeing reduced the cost of production, and high on their list was the elimination of titanium parts where possible. The frame around the cockpit windows, for example, were initially made out of titanium, but were changed to aluminium with a special coating to prevent corrosion, while some parts that were originally titanium were changed to composites, like the door frames. Other improvements were sought to make the manufacturing process for titanium less costly. Many metallic parts used on aircraft start off as large blocks of metal that have to be machined down into their final shape. This results in a ton of wasted metal as the metal is gradually shaved away. Aircraft manufacturers quantify this wastage with something called a buy-to-fly ratio, and it's a huge source of increased manufacturing costs. Costs that Boeing has tackled by collaborating with Norsk Titanium, a titanium 3D printing company. Now, making 3D printed metal parts is not easy. Most titanium 3D printing involves a powdered titanium that is melted together using lasers. Researchers used high-speed X-ray imaging to visualize what happens during this process and found a lot of imperfections. The track varies in height, the powder gets blasted away, resulting in varying thickness and separated tracks, and even bubbles form, causing pores in the metal. This creates parts with a lot of micro-imperfections, and imperfections lead to decreased life as fatigue causes cracks to form. We can visualize a material's fatigue strength by plotting on an SN curve, which places the magnitude of the alternating stress on the y-axis and the number of cycles it survived on the x-axis. For traditional machined titanium, it looks something like this, whereas for 3D printed parts, it looks like this. 3D printed parts simply fail much sooner because of these tiny imperfections. Norsk has worked to improve this. Instead of using laser sintering with powder, Norsk have developed a revolutionizing, patented, wire-based metallic 3D printing system for titanium that they monitor with 600 frames per second cameras for quality control. These 3D printed parts are then machined down into their final shape, reducing the total titanium used by 25 to 50%, and their printing method is 50 to 100 times faster than the powder printing method. This process resulted in the first ever FAA certified 3D printed structural components, and they first flew in the Boeing 787. This plane is truly innovative. Titanium.
Grammarly Go is the only generative AI product that you need. It's easy to use in the places you write. With one download, you get the power of generative.
Was not the only material Boeing worked on removing from the plane's construction to save on cost. Copper once formed an important part of the 787's wing, where it was laid down in thin strips on the wing's surface. This is not a typical design choice for aircraft wings, and once again, it was influenced by the 787's composite construction, because composite materials are not good conductors. Carbon fibers are great conductors, but problems arise because of the plastic resin binding them together, as this resin is an insulating material, preventing the passage of electricity, which is a massive problem for planes as getting hit by lightning is not a rare occurrence. One study calculated that lightning strikes occurred once every 3,000 hours of flying between 1950 and 1975. A 787 was struck by lightning while taking off from Heathrow. Upon landing in India, 42 to 46 holes were found in the fuselage as a result of resistive heating. The plane survived and was flown back to London for repairs with no passengers aboard, but composites' vulnerability to this kind of damage is a drawback, and the repair process is more complicated than with aluminium. However, this strike could have been much worse. If the electricity does not run smoothly along the surface of the plane and exit, it may cause a spark in the fuel tanks and cause an explosion. This kind of accident was not uncommon in the early days of the airline industry. Pan Am Flight 214 was struck by lightning while it flew in a holding pattern, waiting for a lightning storm to pass at Philadelphia International Airport in 1967. Its left-wing fuel tank exploded, causing the plane to barrel out of control to the ground in flames. Since then, the aviation sector has implemented rigorous safety measures and lightning protection tests to ensure an accident like this could never happen again. Early 787 wings were designed with copper strips to ensure the electrons had a path of low resistance along the surface of the wing, ensuring they wouldn't travel to the fuel tank and cause a spark, while also preventing resistive heating damage to the composite structure. Fasteners were sealed with an insulating material to stop electricity from traveling down the metallic fastener into the fuel tank, and the fastener themselves were fitted with compression rings and a sealant to eliminate potential spark locations caused by gaps and sharp edges. Finally, the 787 has a nitrogen inerting system that fills the tank with nitrogen. Ignition can't happen without oxygen. Boeing has since removed 2 of these protections in a cost-saving measure, removing the copper mesh and insulating caps, which drew concern and criticism, but Boeing argues that between the nitrogen inerting system and the other safety measures, these expensive features were not needed. Where composites couldn't be used, other materials were chosen. The leading edge of the wing and tail, the tail cone, and parts of the engine cowling were all made from aluminium or other metals. The leading edges of the plane needed aluminium because of composites' poor impact resistance. While composites have extremely high strength, they can be brittle on sudden impacts, such as bird strikes, which most commonly happen at the leading edge of the wing or on the engines. Metals are able to deform on impact with a reduced chance of fracture, instead of shattering as composites would. Aluminium leading edges were also beneficial for the purpose of de-icing because it is a good thermal conductor. If you have ever flown on a very cold day, you may have seen a truck spray fluid onto the wings of the plane. This is de-icing fluid, a heated mixture of glycol and water. It's needed because most planes aren't capable of de-icing themselves on the ground. The 787 can when fed with external power because it uses a new type of de-icing system. The 787 uses electrically heated blankets bonded to the surface of the slats, which are able to heat the surface of the wing and melt or prevent any ice formation on the leading edge of the wing. Traditionally, ice is prevented by extracting hot bleed air from the engine and piping it to vulnerable areas such as the leading edge of the wing, where ice buildup could severely interfere with the wing's operation. This draws valuable energy away from the engines and increases fuel consumption, while also requiring a complicated network of tubing and exhausts which add weight and increases complexity of construction and maintenance. The electric heating system is twice as efficient as the extracted bleed air system, as no excess energy is lost through venting air to the atmosphere, and it also reduces drag as the exhaust holes for the bleed air on the lower side of the wing create drag. The 787 is actually the first commercial airliner that has eliminated this bleed air system, which was a huge technical challenge and required a complete redesign of several systems and an entirely new engine. In our next video, we are going to explore the incredible engineering behind the power systems of the 787, exploring the advancements in the jet engine and the overall system architecture that allowed the 787 to become the most efficient long-range airliner ever made. We will be releasing that video here on YouTube shortly, but if you don't want to wait, it's already on Nebula ad-free. Or if you are like me and like to sit back and watch longer videos, we have created a special hour-long version that combines both videos and has extra information that didn't fit into either of the YouTube versions. I've included links to both of these videos in the description for those of you already subscribed to Nebula. Or if you have yet to start support, Real Engineering is brought to you by the Curiosity Stream and Nebula Bundle Deal. Sign up now to watch the hour-long version of this video linked in the description. Jet engines are a marvel of engineering. From precisely controlling the internal atomic structure of metals to create turbine blades that are actually one single crystal, to delicate robotic machining that humans could only have dreamed of a decade ago. The jet engines of today are barely recognizable to those of the 1940s. They're bigger, they're more powerful, and they're more efficient. The Dreamliner's engines are so big that they are the same diameter as the 737 fuselage. And this is just part of the puzzle that has allowed the 787 Dreamliner to break world records. In March 2020, in the midst of a global pandemic, the US government imposed travel restrictions on all European travelers, a move that cut off France from one of its far-flung territories in French Polynesia. Business as usual for Air Tahiti was no more. A creative solution had to be found to replace their regular flights between Tahiti International Airport and Charles de Gaulle Airport, which, under normal circumstances, stopped over in LAX. Faced with disruption, Air Tahiti began operating the world's longest flight, a 16.5-hour, 15,700-kilometer non-stop flight between Tahiti and Paris, the world's longest distance scheduled flight, and it was technically a domestic flight. The 787 made that possible, and today we are going to learn how. In our last video, we explored the incredible engineering that has gone into sculpting the airframe of the 787, but all of that work is useless without a power system to match. Boeing transformed the way airliners are powered to create a plane like no other. The first step in powering a large plane is to get the jet engine started, and that itself is a very power-hungry process. We need to get the compressor section turning in order to achieve adequate compression for engine ignition. We have all seen footage of people hand-cranking old piston-powered planes to get them started. This obviously is not feasible for jet engines, which need to rotate at very high speeds to start. Engineers have dreamed up many ways to complete this job. Some engines use explosive cartridges that look like shotgun shells that will be fired by an electric charge. The hot gas is expelled by the cartridge, then drive a smaller turbine, which is connected to the drive shaft through a reduction gear, allowing the smaller turbine to get the engines up to speed. Cartridge starters were popular in older military planes that may need to get into the air on very short notice with limited ground support. Some planes, like the SR-71, had a direct drive starting cart, which connected two massive V8 engines directly to the J58 engine from underneath the nacelle to get the powerful jet engines to 4,500 RPM. However, air starting is by far the most common method, where pressurized air is fed into the turbine section directly to get the engine moving. This can be done with an external cart called a hover cart, which connects hoses to the engine. But most commercial airliners are capable of generating their own pressurized air with an APU, or Auxiliary Power Unit. These are smaller turbine engines located at the tail of the aircraft that are small enough to get started with a battery and an electric motor. Most people aren't even aware this mini turbine engine exists, but you can see the exhaust here on all modern commercial airliners. The 787's APU, like other planes, is started by a small battery, but from here, the 787 system architecture is very different. The 787's APU, like other planes, is started by a small battery, but from here, the 787 system architecture is very different. The 787's APU does not provide pressurized air to the engines. It provides electric current to two electric motors attached to each engine, which act like the starter motors on your car. However, these motors can act as generators to provide the 787 with unparalleled electric power. A traditional plane has one generator on each engine and one on the APU, but the 787 is anything but traditional. There are, in total, 6 generators on board, with 2 pairs on each engine, providing the main power. each capable of generating 250 kilowatts, with 2 more on the APU providing secondary power, each capable of providing 225 kilowatts. If all 6 of these generators were running at the same time, that would be 1.45 megawatts of power available to the 787, 4 times more than a 777 is capable of producing. To put
Listen, there's a good chance somebody's trying to hack your website right now. You gotta make sure you're...
that into perspective, this is a 787 on a football field. If we needed to generate that electricity with solar panels in the middle of the day, we would need to cover about 10 football fields with solar panels. This is a lot of power. So why did the 787 need that much power, and where is it all going? The 787 uses a no-bleed air architecture. Traditionally, many aircraft systems are powered by hot, compressed air drawn from the compressor section of the jet engine. The APU normally provides hot air to the engines to get them started, and then, once the main engines are started, hot compressed air bled from the compressor section drives several important systems. Normally, air conditioning and cabin pressurization is handled by the bleed air system. The bleed air would be drawn from the engine at a temperature upwards of 230 degrees Celsius. This obviously would quickly turn the cabin into an oven, so the air would first run through a complicated air conditioning and pressurization system, where some of the air is cooled using a heat exchanger, which uses outside air from a surface-mounted intake called ram intakes to remove heat from the engine bleed air until it is a suitable temperature to be distributed through the cabin. So, we are doing work to remove energy from this valuable bleed air from the engine. This is obviously rather inefficient, and all that ducting is heavy. And this is why the 787 does not use this system. Its cabin pressurization is handled entirely electrically. We now have 2 inlets, the ram air inlet and the cabin air compressor inlet. The cabin air compressor leads to, you guessed it, the cabin air compressor, an electrically driven device that compresses the air for the passenger cabin. This compression process heats the air up too much for direct use into the cabin, so it does require some cooling using a heat exchanger cooled by the ram air inlet. You can see this little door open while the plane is on the ground, and it serves to protect the inlet from foreign objects entering it. Another energy-intensive process that has been handed over to the electric motors is the braking system. As you can imagine, the energy required to slow down a 200-ton plane traveling at 270 kilometers per hour is not small. Calculating the energy required is pretty trivial. We just need to calculate the kinetic energy of the object, which we can do with this equation, and that gives us a kinetic energy of 562 million joules. That's a lot of energy, and the vast majority of that energy needs to be dissipated by the brakes of the plane. Reverse thrusters can deploy that redirect air from the bypass ducts through slots that open on the side of the engine. So, the brakes need to convert a lot of kinetic energy into another form of energy, heat energy. You can really see this in effect during a plane's most extreme brake test, an aborted landing test. Here, the plane is flying at full load, including the weight of the fuel, and has to abort at its V1 speed, the absolute maximum speed a plane can abort a landing at. Beyond that point, the plane has to take off. When the plane comes to a full stop, the brakes are glowing red hot. Typically, the braking mechanisms of planes is driven by hydraulics, with a hydraulic piston forcing the brake pads against the wheel to slow down the plane. The 787 removed this bulky hydraulic system and traded it in for brakes actuated by electric motors. Each of the 8 landing gear wheels feature one of these units, and together they helped eliminate between 62 to 111 kilograms of weight from the 787, while also being drastically easier to maintain and install. The 787 does have a hydraulic system, however, but it has eliminated 2 large bleed air-driven hydraulic pumps that are normally used to meet peak demand during takeoff and landing, where landing gear actuation and deployment of high-lift devices like slats and flaps would overload the other pumps that power the hydraulic system during cruise. The 787 had the added electric power needed to rid itself of these bleed air powered pumps and replace them with more efficient electrically driven pumps.
Worried texting won't be as fun if you switch to Android?
Boot, the 787 is able to generate higher hydraulic pressures that allow it to use smaller hydraulic components, which saves both weight and space. So, that covers most of the system architecture, but we haven't even touched on the revolutionary engines themselves. The Dreamliner is most commonly fitted with two General Electric GE and X engines, each capable of producing between 310 kilonewtons and 360 kilonewtons of thrust, about the same thrust that General Electric's previous generation engines, the CF6, equipped to the 767, were capable of producing. But the GE NX produces this thrust while consuming 15% less fuel. That's an incredible leap in technology. The GE NX achieves this primarily through two major design features that were not possible with older engines. The first is a gigantic bypass duct that surrounds the main engine. The primary components of modern-day jet engines are the fan, a compressor, a combustor, a turbine, and a nozzle. The ultimate goal of a jet engine is to draw in air and pressurize it as much as possible, which increases the energy potential of the air before mixing it with fuel and igniting it, causing a rapid expansion and acceleration of air. The work done by the compressor is then recovered in the turbine section, which powers both the compressor and the fan. Finally, the air, with its remaining kinetic energy, travels through the nozzle, where it is accelerated more and sent out the back of the engine to provide thrust. The engine core, this part of the engine, is what powers the engine. Yet, most of the air that travels through the GE NX bypasses this section completely, only passing through the fan and through this bypass duct. And this is one of the reasons the engine is so incredibly efficient. Bypass ratios have continually increased over the years, which is one of the reasons engines keep getting bigger. The GE NX engine has a bypass ratio of 9:1, meaning for every kilogram of air that passes through the engine core, 9 kilograms flow through the bypass duct. This is extremely high. The engine the GE NX replaced only had a bypass of 5.7, which, during its time, was itself a very high bypass ratio. While the core takes a small volume of air and accelerates it rapidly, the fan takes a massive volume of air and accelerates it just a little, while not requiring it to be mixed with fuel and ignited. This drastically increases the fuel efficiency of the plane. The fan essentially acts like a gigantic propeller. The industry has been aiming for larger and larger bypass ratios for decades, but there are a couple of limiting factors that make it difficult to increase the size of the fan blades. The compressor and fan are driven by the same shaft, meaning they rotate at the same speed. But because the fan is so much larger than the compressor and turbine blades, the fan experiences much higher centrifugal forces, and if the fan blades grow too long, their tips could even break the speed of sound, leading to shockwaves and a massive increase in drag. The first problem we need to address is how to handle those centrifugal forces. The magnitude of the centrifugal force can be found using this equation, where m is the mass, w is the angular velocity, and r is the distance from the center of rotation. So our force will increase with the weight of the blade, the speed of its rotation, and its diameter. We want to increase our diameter to increase our bypass ratio. So we need to figure out ways to either decrease our weight or decrease our rotational speed. The GE-NX achieved the first requirement by using lightweight carbon fiber fan blades. Older fan blades were constructed from titanium being used for its excellent strength to weight ratio. But carbon fiber blades have an even higher strength to weight ratio, while also being much stiffer than titanium, allowing the carbon fiber composite blades to be longer and thinner than their titanium counterparts. This form factor even allowed General Electric to reduce the blade count from 22 to 18. In all, this resulted in a 15% weight savings in the blades, allowing them to spin faster without worry of damage. However, composites do have one huge drawback: their impact resistance. One of the tests engines need to pass to reach certification is the chicken gun test, which, as you may have guessed, involves yeeting a dead bird into the engine and seeing how it holds up. The fan blades are the first part of the engine any foreign object will encounter, and thus need to be capable of withstanding the impact. Early development of composite fan blades by NASA and GE showed that composite blades by themselves simply were not up to the task. To solve the issue, the leading edge of the blades are reinforced with titanium. Bypass ratios are likely to continue growing as our technologies develop. Speed reduction gears between the main drive shaft and the fan may allow engine manufacturers to increase bypass ratios even more. Pratt & Whitney employed this technology in their PW1000G engine to achieve the largest bypass ratio ever seen in a commercial airline turbofan engine. They included a planetary gear between the main drive shaft and the turbofan drive shaft, which applied a 3-to-1 reduction in speed, allowing the turbofan to spin at a lower 4,000 to 5,000 RPM. This enabled the fan to grow in diameter, as the forces the larger blades had to endure were drastically reduced with a lower speed, giving the engine a record-breaking 12.5-to-1 bypass ratio. General Electric considered the design for their new LEAP engine currently in use by the 737 MAX, but problems with weight and maintenance of the planetary gearbox deterred them, and that hesitance may have been justified, as the engines have had a turbulent operation history with several groundings and engine removals, although these issues were not directly a result of the planetary gears. However, as the technology improves, we may see more of these geared designs being used to drive even greater fuel savings. The next design feature that helps the GE-NX to reduce fuel consumption is the extremely high compression ratio achieved through the engine's compressor section. Compression ratio is the ratio found by dividing the pressure at the exit of the compressor section by the pressure at the inlet. This one variable has huge implications for a plane's fuel efficiency, and just as we can see a clear upwards trend for bypass ratios over time, the same can be seen for pressure ratios. The reason for this is fairly simple. By increasing the pressure ratio, we can maximize the energy we can extract from our fuel, because there is more useful energy available for extraction in our turbine and nozzle than if we compress the air less. But it's not quite as easy as just increasing pressure across our compressor. In order to achieve higher compression, we may need to increase the number of compressor sections, which will increase the weight of the engine, which will increase fuel consumption and reduce the advantage. Higher compression will also lead to higher temperatures, which may cause material failure in the compressor blades. And perhaps most critically, increasing the temperature results in increased emissions of potent greenhouse gases like nitrogen oxides. Nitrogen oxide formation rates rise exponentially with flame temperature to break down nitrogen molecules in the air and allow them to combine with oxygen. To facilitate increased pressure ratios while hitting climate change goals, This problem had to be addressed, and they did it through ingenious fuel injection technology. The compressor feeds its high-pressure air into 22 fuel mixing nozzles located in a ring around the compressor exit. Their job is fairly simple: mix the fuel into the air and ignite it. A simple job that started development in 1995 with both General Electric and NASA. The art of crafting the perfect fuel injection nozzle is incredibly complex, a delicate yet violent process, like an orchestra whose crescendo is a fiery explosion. With the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. So how does it avoid those dangerous nitrous oxide emissions?
This all-new Aria is an elegant EV.
Yeah, with 389 horsepower.
By carefully controlling the air-fuel mixture ratios to control flame temperatures. If we plot flame temperatures against air-fuel ratio, we get something that looks like this: the max flame temperatures occurring at stoichiometric air-fuel mixtures. That is, the mixture where air and fuel are both entirely consumed in the reaction. This is the zone where nitrous oxide emissions are highest because the flame temperature is highest. To minimize nitrous oxide emissions, we can aim to be over on this side of the curve with a rich air-fuel mixture. But that would result in a lot of wasted unburned fuel. So instead, we aim to be over here on the lean side of the graph. If we map the combustion process for GE's previous injector, fitted to over 22,000 CFM56 engines, we would see the air-fuel mixture is initially injected in this zone, with a rich air-fuel mixture. Then it goes through a dilution process to reach a lean mixture where the fuel is fully consumed. The issue with this is that the fuel goes through the stoichiometric region in between these two phases, creating a great deal of nitrous oxides. The TAPS fuel injector looks like this, with a central main pilot surrounded by a ring-shaped main injector, creating two swirling airflows that look something like this, which uses a large amount of air in the pre-mixing phase to ensure thorough mixing and a lean air-fuel mixture. If we map the combustion process of TAPS, it starts in the lean zone and gets even leaner further into the combustor, never getting close to the peak nitrous oxide production region. This may seem like a simple device, but it took generations of design iterations with computer simulations, gradually bringing the engineers closer to their target. And none of their designs would have been possible without current generation metallic 3D printing that could manufacture the complex parts with the materials capable of resisting the enormous heat within the combustor. 26 years of development paid off with 60% nitrous oxide emission reductions, a fuel injector compatible with the record-breaking 58:1 pressure ratio used in the GE NX. GE managed to increase the pressure ratio even though they reduced the number of compressor stages. Each of these turbine discs is one stage. The GE NX contains 10 stages, 4 fewer than the CF6 engine it is replacing. GE managed to do this through new improved blade design, which is a lot less info than I wanted to share, but finding information on this topic was incredibly difficult, a testament to how advanced and secretive the technology is. The compressor does include 3 blisk stages, which are perhaps the most impressive feats of machining I have ever seen. Traditionally, compressor stages are made by attaching the blades to a separate disc with dovetail connections. This decreases manufacturing complexity, but the dovetail connection is less durable, increases assembly and maintenance costs, and allows some air to escape through the connections. Blisks are compressor stages that are manufactured from a single piece of metal, making them stronger and easier to install, while improving aerodynamic efficiency. Improving aerodynamic efficiency was the name of the game to improve compression ratios. And of course, that needed to apply to the turbine section that powers the compressor. It too benefited from cutting-edge aerodynamic modelling. The turbine also made use of new material science breakthroughs, being the first commercial engine to make use of gamma titanium alumini, an advanced alloy of titanium and aluminium that combines the heat resistance of titanium with aluminium's weight savings, replacing the nickel alloys of past. It took 3 decades to take this material from the lab to commercial use, and the Dreamliner was the first plane to make use of it, paving the way for the material's acceptance in the industry. All of these factors combined to allow the GE NX engines of the Dreamliner to reduce fuel consumption by 15% over previous generation engines. That is an astronomical leap, and on top of all that, the engine is 60% quieter than similar sized planes. In part, thanks to the engine's most distinctive feature, this sawtooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons, and they aren't just futuristic cosmetic design, but functional parts of the engine that significantly reduce engine noise.
So you think you know Wix, but do you really? First up, we've got Shake video masks. You can use different
What different? difference can a mere shape change at a nozzle exit have on the overall noise pollution produced by the aircraft? Because turbofan engines force air out of their bypass chambers and turbines at speeds that are much higher than the speed of the ambient air, the air interacts with the free stream air, causing mixing. This mixing causes uncontrolled vortices, which in turn generate excessive noise for both the passengers and the community on the ground. Think of it like water accelerating down a waterfall and striking the water below. That turbulence can be extremely loud. the chevrons aim to control the vortices that are shed from the engine nozzle by creating smaller vortices at each of the teeth of the chevron to allow the hot, fast air being expelled from the engine to mix with the ambient air more gently. This is said to reduce jet blast noise by as much as 30% and allowed Boeing to use substantially less sound insulation in the fuselage walls of the aircraft, which helped to reduce aircraft weight. The 787 truly does live up to its name. It provides a passenger experience that is almost incomparable to that of other commercial aircraft, with advances in noise reduction, fuel efficiency, and passenger comfort. This series is usually saved for aircraft and technology most of us will never set foot in. But the 787 could be the most advanced piece of engineering we have ever covered, and it's a plane many of us will have the opportunity to fly in and marvel at the decades of engineering advancements that made it possible. This nearly half-hour-long video is just half the story, but the full hour-long director's cut version has been available on Nebula for over a week. It combines the two halves of this video released on YouTube into one seamless, ad-free experience that you can sit back and relax to watch. I removed one section from this video detailing the complicated thermodynamics explanation of why compression ratios actually increase efficiency, because it felt just too academic for YouTube. But I think die-hard fans of this channel may enjoy listening to a 10-minute explanation of temperature entropy diagrams. The director's cut also includes explanations of the 787's nifty electronic heads-up display in the cockpit and electrochromic window shades. I felt neither of these topics really fit in anywhere in the larger script. Nebula is the best way to experience
I just realized. So that was a really fun topic to hit at. We are starting 100% after like 2 points, but yeah. Let's look at our ETA. We have 21 minutes until arrival. So enjoy that before we head into Fiji. Oh, and we are doing the now. I think we are. Let me look. Let's look at the weather actually. Oh, look at that. We escaped perfectly on time. Because now it's past rain. Okay. 3:30, 3:30, that's 8. But what did it? Yeah. Cool. So let's set up the thing here for our arrival into Bora Bora. Cool. Yeah. Okay. That's cool. Yeah. Okay. Let me put my arrival. That's I think everyone out of there. So once we get 85 done, okay, that was pretty done. Hold on, I'll check case. Okay, I want to walk this. No worry. No. Good. South. 4, 7, 5, 3. One, 7, 1, 9, 3, 13. And what's down? 3. Okay. Here's up. Here. Here. Okay, good. Yeah. Alright. I'm defeating you. Close. Let's listen to the music. Now. Yeah. Okay.
Looking for the best music for your videos? Then you should check out Artlist.
Alright. It's for all of the 8 people that have joined. Don't remember, guys. You guys can talk and chat with us want to. Oh, the over. Oh, what's great. You guys can chat, message, whatever you want. And I'll look at the message. I'm so happy. So excited today. I'm so excited. Alright, all started to set in time now. One just burned files, which is coming up really soon. So here close the DVD boxes. 350 on the altitude, which is 350 on speed, and 1,000, 3,000 here. Full air. And I'll make sure it's 10 right fire. Alright guys, here we go. Let's see it landing. And it made it out. That's a big turn on the light. Alright, 85, there it is. Throttle, vertical speed, altitude, firing, and restart descent. What's that audio? Alright guys, on down we go. Alright. Down we go. We have officially started our descent and okay. Here's what it says. We had a reflux from up, one street down, and one street down. So, yeah, that's fun. And what are these together? So, next week, we'll probably experience the Microsoft Flight Simulator 2020 experience by probably be somewhere in either Thailand's coast in San Francisco, California, or we'll go from Orlando to Orlando all the way down to Cancun. That might be a good flight to do. But yeah, 10 minutes until arrival. And we're still descending. Let's see if we can find land. No land still, but that will change very shortly. Give or take. Alright. We're gonna go back to the and we're still descending so you guys can still hear take the audio. Okay, audio sounds good. Yeah. Alright, we've been live for about 2 hours. Alrighty, so guess that's good. Let's see, is there land? Oh god. Yes, there is. It's a small island. see everybody. I see land at 11 o'clock. And we're turning. Also, it's on. There's something. Yep. There's right there. We can see it. Right in front of us. Touch the screen sound. Okay. We're at 30,000 feet. Got an 87 nautical miles remaining. Our PLR should probably guys. Yep. With our phone. 240. Then we want to max party. Let's go on. Okay. Alright, let's see here. Around. Yep, it's too low. But I'm not right now. Here. We done over someone overlay. Yeah, overlay. There's all of them. Right? I'm stuck. There's not close to something more. It will be 300 on the speed. And we just like this. What I'm about. Okay. We're officially landing, and there's a mountain right above us. Alright, ladies and gentlemen, welcome to Fiji. Looks beautiful over here. Yeah. I don't know. You're not as much of my phone. Yeah, sure. Well. Honestly, at this point, let's start picking up this one again. Yeah. And it's probably sending again. Let's put up this.
The University of Arizona Biosphere 2 is the world's largest controlled environment dedicated to studying and solving the problems facing our planet's...
Sync. Yeah. Okay. Yeah. Let's just start with our pick it up. Anytime now, great. Alright, sure, that's right. One. Yeah. Let's just read it. I'm not sure what yeah, so what is the general direction? Okay. Well, we're going. Let's go 360 speed. It's recording. Over the island. Back up. Alright. 175.
We get it. Back to school.
And we're going to start the physics. 20 tons. Right now. I want to make sure that we capture where I land. 1119. That one. Alright, cool. Wait, it was 11. Oh. I was wondering why we never got data out of this. Okay. 30 and 25. And let's just make let's go 70 degrees. Now let's door and glide. Check that first. We are almost ready for airport should be off on the coast. Alright. Once the localizer comes in, we'll capture it and capture the flight atmosphere. Okay. Once the localizer is look. Localizer capture. And we're ready. Flying. And fly. Capture. Glide zone is captured and localizer is captured. We're ready to land. Here now. Alright, I'm gonna turn off the sound. Here now, all greens. Let's go. Cool. Alright, oh, there's one thing I forgot to do. Stepping out of the tower, which was 10, 1, 2, 3, 2, 1, set. I'll just get him. Look at that landing. Look at that bird. That looks awesome. Okay. It is really strong. Alright. 800 feet. And keep going at 10 degrees. Hi, bird. At night. Checked. Continue. Checked.
200.
Autoscope off.
100 feet. 50. 50 feet. 40.
Oh.
20. Contact.
Versus. We'll still have X play, but you know, today's the last day where we fly. I have Starlight, and we'll be flying Microsoft instead. Welcome to the okay, replay and call it a day. Alright, what's this? First, I want to actually yeah, that's okay. Now, profile back. We're gonna grab here. Yes. Check. Okay. Gonna check. I'll break. Alright. Cool. And everything should be good. Oh! Everything almost. Reverse. Yeah, one. Cool. Alright. Let's look at that beautiful dinosaur. I'm gonna bring you guys one more thing I'm gonna look on. One more planning, one more replay, and then we'll call it day. Yeah, so bye bye. And now the fighting. Go. Go away. Turn off the sound. That's I'm just gonna get my nice safety briefing, everything like that, and then we'll go on. Alright, so for anybody that was here, thank you for coming and watching the live stream today. We'll be off of X-Plane until we won't be streaming until Friday. Our next stream will not be in X-Plane, it will be in Microsoft Flight Simulator 2020. So I'm going to be removing X-Plane after the stream, which that's going to be bittersweet for me, but and we'll be in an Airbus, which is completely different from a Concorde, Boeing, what we've been flying. So I hope you guys enjoyed this replay. One last replay about to do in the Concorde. Seems fitting. Let's do it.